Hello, everyone. I wanted to make a video for you. I don't think I'm going to get to one and inverse functions in class. Um, Most students struggle with one-to-one and inverse functions less than the composition and rational functions. So I really want to spend the majority of our class time on the things that more people tend to struggle with. That doesn't mean that you won't struggle with the one-to-one or the inverse functions, but I think it's more doable for you to kind of work through this. So that's kind of the why I made the decision that I did. And I wanted you to have this resource in case you needed it. So a function is one-to-one if. Now, the word function here is a loaded word. This means something very specific in mathematics, and we talked about this in module one. A function is a relationship, a mathematical relationship, in which your x's can't cheat, right? Every x has to have only one y. Now, a function, so each x has only one y, is one to one. The word one to one, you don't have to be a function to be one to one, but we're going to be talking about functions in this class. Um, and so one to one means that each output, that means each y value, is connected or related to only one input. Basically, what this means is that your y's need to be in committed monogamous relationships. It's the same as a function, only now we're looking at y's instead of x's. So to be one to one, your y's cannot be cheating. Um, a function means your x's can't be cheating. One to one means your y's can't be cheating. Graphically, a function is one to one if it passes the horizontal line test. The horizontal line test says if any horizontal line can be drawn that hits your graph at more than one point, then your graph is not one to one. Okay. If any horizontal line can be drawn that hits your graph at more than one point, your graph is not one to one. Again, if you draw a horizontal line that fixes y, if it hits your graph at more than one point, that means that single y value is dating more than one x. That means that y is cheating and you are not one to one. Okay, so we've got some functions down here, and we need to figure out whether or not each one is one to one. All right, so to figure out whether we're one to one, we have to look at our y's. So in this table in number one, do we have any y's that are cheating? We do, don't we? Y equals -7 is dating two different x's. It is dating both x equals -1 and x equals -3. Y equals -7 is cheating, and this is not one to one. All right, let's come to number two. Does this pass the horizontal line test? Do I have any y's that are cheating? It does not pass the horizontal line test. I've got y equals 3 is cheating. I also have y equals 0 is cheating. That means that this is not one to one. I've got two y values that are cheating. And then how about in number 3, is this one to one? Well, I'm going to look at horizontal lines, pretend these are all horizontal. All of these only touch my graph at one point, right? Just 1 point for every single one of these. Yes, this is in fact 1-to-1. It passes the horizontal line test. Okay, so that's what 1-to-1 means. Now, why do we care? Well, we care because if a function is 1-to-1, then it has an inverse. That's really why we care about 1-to-1. If you have a function that is 1-to-1, then that function has an inverse function. So now the question is, what's so great about an inverse function? What is it and what does it do? Well, an inverse function is basically a function that reverses another function. And the way that it does this is by switching x and y. This is the big thing that we need. An inverse function switches x and y. Now, why we care about inverse functions is because solving. In order to solve a function, we often need to utilize inverse functions to undo another one. For instance, if you're solving x squared equals 4 and you want to solve this, you take the square root of both sides, right? Now, the reason that you can take the square root of both sides is because the x squared function and the square root of x function are inverse functions. They undo each other. So when you take the square root of x squared, they undo each other and you end up with just x. They kind of get rid of each other. So that's really what an inverse function is used for. We use it often for solving. Um, and so that's really why we want inverse functions. Um, and the way that inverse functions work is that they switch x and y, they undo each other. Now, by switching x and y, what I mean is that if I have f of x equals y, then the inverse of that, f inverse, would start at y and it would take you back to x. And you can go back and forth between these all day. From one function to the other, you just switch the placement of x and y, right? So if our forward function f takes us from x to y, our inverse or backwards function takes us from y to x. And if we compose a function and its inverse, we talked about function composition earlier in this module. If you plug the inverse into the original, they undo each other and you end up right back at x. And similarly, if you plug your original into your inverse and compose them this way, again, they undo each other and you end up right back at x. A function and its inverse undo each other. And then the last thing that I want to make note of here with inverse functions is that the domain of my inverse function. The domain of my inverse function. Those are the things that go into your inverse function. Well, those are outputs on my original function. And if it's an output in my original function, that was part of the range of my original function. So the domain, the things that go into my inverse, is the range, things that came out of my original. And similarly, the range of my inverse function, the things that come out of my inverse function, well, those were x values that went into my original function. That means the things that come out of my inverse, my range, is equal to the domain, the things that went in to our original. So x and y switch, and so do the domain and the range. Okay, so that's really what an inverse function is, and some facts that you'll need about those. Now, if I give you a function, how do you find its inverse? Well, we're going to be finding inverses by doing what inverse functions do. Inverse functions switch x and y. So to find an inverse, you are going to switch x and y. Okay, so the first thing that you're going to do is you are going to replace f of x with y in your original function. This is just so that your brain can see where y is. um, and that way, when you go to switch x and y, it'll be easier to see where y is. If you don't do the first step and replace f of x with y, it just might be harder for your brain to see where y is. But the big thing that we need to do here is switch x and y, because that is what our inverse function does. And when I say switch x and y, I want you to replace all x's with y's and replace all y's with x's. You're just going to Freaky Friday switch the x and the y, switch the places that they're in. So any x becomes a y, any y becomes an x. And as soon as you switch x and y, you are in inverse land. That is your inverse function. But when we write functions, we write y equals. So after you switch x and y and you're in the inverse function, I want you to solve for y to write y equals, because that's really how we write functions, right? You want to get y equals. So we're going to do the same for our inverse function. And then you can, again, this is just for our brains, you can replace y with f inverse of x. That way your inverse function is labeled for you. Okay, so let's try this. Number one, f of x equals x plus 1, that quantity squared, and it tells us that the domain of my original function is from -1 to infinity. We'll get there in a bit. So that's the domain for this function, and we need to find the inverse function and state its domain. So I first need to find my inverse function. To do that, the first thing that you're going to do is replace f of x here with y. That way your brain can see where y is. And now, once you've got y in there, I want you to switch the place of x and y. So y becomes an x becomes a y, right? Freaky Friday switch. They switch places. All right. And now we are in the inverse function. This is inverse function land, but we need to get y equals, because that's how we write functions. So in order to get y equals, y is right here, I need to get rid of this squared up here. So I am going to take the square root of both sides, because that's the inverse function of a squared. That's going to get rid of this. And I am going to get the square root of x over here is equal to y plus 1 over here. And so now to get y by itself, I'm going to subtract 1 from both sides, and I'm going to get the square root of x minus 1 equals y. And that is my inverse function. So I'm going to relabel that as f inverse of x. My inverse function is the square root of x minus 1. And then I have to find the domain of that. So to find the domain of this, we can apply our domain rules. I have a domain rule for fractions, I've got a domain rule for roots, and I've got a domain rule for logs. Here I've got a square root, so I'm going to apply the square root rule. The square root rule says that the stuff under the radical, here the stuff under our radical is just x, and that has to be greater than or equal to 0. right? Because that's what our domain rule says for square roots. And specifically, because it's a square root, my index is a 2. It was an even root, which is why we did that. The stuff under your radical has to be greater than or equal to 0. If it had been an odd root, your domain would be negative infinity to infinity. And so for greater than or equal to 0, that means we go from 0 to infinity, and we're closing that. Right here, it's a bracket on 0, sorry. We're closing that interval, there we go. And then something to notice here, this is going to come in later. This domain, this is the range, or it should be the range, of my original f of x. Well, x plus 1 squared. This is a y equals x squared graph, which looks like this, right? But this plus 1, because I'm adding 1 inside with x, this is going to slide us right and left. Inside goes the opposite way you think it will, so this is actually going to slide us left 1 unit. So I can move this to the left 1 unit. This is what my graph looks like. My original f of x. And so it's an x squared graph slid to the left one. The domain of this is negative infinity to infinity. They cut this down a little bit, and that's because of the range of this guy. But anyway, the domain of my inverse is the range of my original, and that goes from 0 on up to infinity. So the domain of my inverse is equal to the range of my original. Okay. Next one. I want to find the inverse function for y equals x minus 3, that quantity to the third. Okay, I'm going to replace f of x with y so that my brain can see where y is. And now I can switch places. Y becomes an x becomes a y. And now I'm going to solve this for x. To solve for y, because I want to write y equals. I'm solving for y here. First thing I got to do is get rid of this to third power. To do that, I'm going to take the cube root of both sides. So I'm going to have the cube root of x over here and y minus 3 over here. And then I will add 3 to both sides. And now I have y by itself, and this cube root of x plus 3 is my inverse function. There we go, that's not so bad. Okay. Try to make it so you can still read that. There we go. That's my inverse function. Now, what's the domain? Well, the domain of this, I have a root rule, right? I have to apply the root rule. The index of my radical here is 3, which is odd. Because I have an odd root, that means that my domain is negative infinity to infinity. I don't have to do any more work than that. And then just a quick check, we have to make sure that this matches the range of my original, which looks like x minus 3 to the third power. Well, this is a y equals x to the third graph, which is a whoop-de-doo, like so. And this minus 3 inside is going to move us to the right 3 units. So I'm going to take this graph and I'm going to slide it 1, 2, 3 units to the right. And I'm going to look something like this. And the range of this graph is negative infinity to infinity, which matches my domain. That makes me feel great. Everything matches and we are good. All right. Couple more here. F of x equals the square root of 3 minus x plus 10. And again, we're told that the domain of this thing is negative infinity to 3. So to find my inverse, I'm going to replace f of x with y so that I can see where it is. And I'm going to switch x and y. And now I'm in inverse land. But in order to solve for my inverse, I need to solve for y, which is right here. So the very first thing that I need to do is subtract this 10 over, because that's the most loosely connected thing. And I'm going to get x minus 10 is equal to the square root of 3 minus y. And then I'm going to square both sides to get rid of that square root. I'm going to get x minus 10 squared equals 3 minus y. And then I will subtract 3 from both sides. Get x minus 10 squared minus 3 is equal to negative y. And I'm going to multiply everything by negative 1 here to get rid of that negative. Distribute this and it'll be negative x minus 10 squared plus 3 equals y. If your brain doesn't like this negative quantity squared plus 3, you can always switch the order of that and write 3 minus your quantity. Right? These two things are exactly the same. And if you want, you can replace y with f inverse of x. You can absolutely leave it the same if you like the negative quantity x minus 10 squared plus 3. You can absolutely leave it like that. But if your brain wants to switch it around, go ahead and do that. All right. Now, we need to find the domain of this. Well, do I have a fraction, a root, or a log? Nope, I don't have any domain rules. So that means my domain is negative infinity to infinity. Because if no domain rules apply, that means everything works. Now let's go ahead and check. This should match the range of my original, which is the square root of 3 minus x plus 10. Well, y equals the square root of 3 minus x plus 10. Well, this is a square root graph, right? Square root graph looks like this. This negative is going to reflect left and right because I'm inside. To the y-axis, there we go. This 3 here, this is plus 3. This is actually going to move us to the left 3 units. And this plus 10 here is going to move us up 10 units. And order matters when we are doing transformations. So we need to make sure that we go left and right first. And then we can do any reflections that we have. And I want you to move up and down last. So from here, I'm going to slide this left 3 units, 1, 2, 3. And then the second thing I'm going to do is reflect this left and right over the x-axis. This point goes from 3 to the left, and it reflects over here to 3 to the right. And then this point is going to stay the same and everything just reverses here. So that's what we look like when we reflect. And the very last thing that I'm going to do here is move us up 10 units. So I'm going to take this green one, the last one that we had, and I'm going to move us up 10 units. Let's just say that's 10. I'm going to start here. I'm going to go up and over this way. So that's what my original looks like. What's the range of this graph? My original graph. Well, the range of this thing starts at 10 and it goes up. I don't have any y values below 10. And so what that means is that my range goes from 10 to infinity. The domain of my inverse needs to match the range of my original. So if you apply your domain rules and it's different than the range of your original graph, you need to discard that original, like discard what the domain rules tell you, and it needs to match your range. The only time that this will really happen is if you have square roots. That's going to be the main time when this happens in um, your functions. So if your original has a square root in it, be really careful and make sure that you check the range of your original square root graph. Okay. And then finally, the last one that we have here, number 4. I just kind of want to go through the algebra with this one. So replace g of x with y all over 1 plus 8x. And now we're going to switch x and y. Y becomes an x becomes a y. And make sure you switch all of your x's to y's. And now we have to figure out how to solve for y. We are in inverse land, but we need to solve for y. I've got y's on top and bottom here. And I also have a rational equation here. So to solve a rational equation, you're going to multiply both sides by your least common denominator, which for these two fractions is that 1 plus 8y. That's our least common denominator, so we're going to multiply both sides by it. And what that does is clears our fractions. This cancels with this one, and it gets rid of that fraction over here. So I've got negative 9y plus 7 left over here. And I'm going to distribute this, so I get x plus 8xy over here. All right, so now I still need to solve for y. I've got a y over here, but I also have a y over here. So to solve for y, I'm going to put anything with a y on one side, anything without a y on the other. I'm going to put my y's on the left, so I'll add that 9y to both sides. And then anything without a y, like this x right here, also needs to move to the opposite side. So those cancel, and I am left with 9y plus 8xy equals 7 minus x. Okay, sorry, that got a little far over. And now everything over here has a y in it, and so I can factor that y out. If I factor the y out of everything on this side, I get 9 plus 8x. Then I still have that 7 minus x on the other side. And now to get y by itself, I'm going to divide both sides by that 9 plus 8x. And so y is equal to 7 minus x all over 9 plus 8x. and that is my inverse function. Okay. So that's what my inverse function looks like. And now I'm going to need to check the domain here. To apply my domain rules, I've got a fraction. Fraction rule says pay no attention to what's on the top, but you have to make sure that the stuff on your bottom, which is 9 plus 8x, does not equal 0. Well, that means that 8x cannot equal negative 9. Subtracted that 9 from both sides. And that means that x cannot equal negative 9/8. Okay, so if x can't be negative 9/8, that means that x can be anything else. Not negative 9/8, but it can be anything else. So my domain here should be negative infinity to negative 9/8, union negative 9/8 to infinity. And then just to check whether or not that matches the range of my original. My original looked like negative 9x plus 7 all over 1 plus 8x. Well, this is a rational function. Everything's factored. There's no factoring here to do. I'm going to get my vertical asymptotes from the bottom. So 1 plus 8x, if that equals 0, 8x is negative 1, and x is negative 1/8. That's my vertical asymptote. I have an x-intercept where the top equals 0, which is negative 9x plus 7 equals 0. That means negative 9x equals negative 7, and x equals 7/9. And to find my horizontal asymptote, I'm going to look at my end behavior fraction. My end behavior fraction is my leading term on top, negative 9x, over my leading term on the bottom, 8x. That simplifies to negative 9 over 8. And that's just a number. As x goes to infinity, that stays as is. So that means my function looks like y equals negative 9/8 at the ends. So that means that my original function has a vertical asymptote at x equals negative 1/8, horizontal asymptote at y equals negative 9/8. And then I have an x-intercept at 7/9, which is right about here. And my function is going to do this. You can plug a number in on the left if you want to, and you'll find that we are below the x-axis and we're over here. And so this is what my original function looks like. And notice my range here matches my domain here. This all matches because this was y equals negative 9/8. The range here matches that. And so this is, in fact, my domain, and I don't need to worry about anything. Again, you'll really only need to find the kind of check that everything matched. When things can go wrong is when you have square roots in your original. That's when you might have to make adjustments to that domain, to your domain rules based on the graph. Okay, I hope that helps with inverses. Have a lovely day, and I will see you next time.